So in the last class, we were continuing with the unit commitment issue associated with thermal power plants, and we were basically discussing the later part of the lecture. We were discussing the concept of spinning reserve. So we took one example, this example with the figure, and we tried to define what is basically spinning reserve. Then we continued with another constraint associated with unit commitment specifically. So that is offline reserve. And we used this figure to illustrate the concept. And then we also mentioned about another important point associated with the unit commitment constraint, that the reserves, whatever reserves we have, either in the form of spinning reserve or in the form of offline reserve, it is better to have it spread throughout the system, okay? Not concentrated on any particular area. Rather, we would like to spread whatever reserve we have, we would like to spread it throughout the power network so that we can have some safeguard against the islanding, okay? I mean, the problem where we have let's say some fault on this interconnection between these two areas, okay, on the left side of the transmission network and on the right side of the transmission network, where both areas have particular amount of load values, 250 megawatts and 100 megawatts respectively. So in case of some fault, if we have to trip this interconnection, then there will be islanding, okay? They will operate separately in a separate manner without any interconnection between them. So in that case, if we don't have sufficient reserve or sufficient capacity here present to supply the demand here, okay, individual demand for area 1, we have to supply then with the help of this generation plus reserve, whatever reserve we have, and also we have to make sure that we have sufficient amount of generation plus reserve for supplying the demand for that area. So let's continue today with one example for a spinning reserve. So let's say we have again two regions, region 1 on the left of the screen, at the top of the screen on the left side we have, this is our region 1, okay? So this is region 1 and this is region 2. So two region system, they have two interconnections between them. So this is interconnection number 1. This is my one interconnection, and this is the second interconnection. And in between, we have included some numbers, numerical values, to represent the limits on the power flow over the interconnection, okay? So that means the interconnection, these transmission networks, which is connecting region 1 and region 2, they have some capacity, maximum capacity that they can allow. If the flow is beyond that, that means you are going to overheat your network or interconnection, and ultimately the network will ultimately melt down due to overheating, okay? So you should not plan to have some flow beyond this under some contingency case or under some faulty scenario, okay? So let us see how this specific value of 550 megawatt is contributing towards understanding the concept of spinning reserve, okay? So let us see. So there is a table. So there is a table at the bottom. So let's go through the table slowly. So the leftmost column gives you the numbers, number of regions. So in total, we have two regions, okay, region 1 and region 2 here. Second column gives us the units associated with particular region. So unit 1, 2, and 3, they lie in region 1, whereas unit 4 and 5, they lie in region number 2, okay? And total number of units is listed here. So we have total 1, 2, 3, up to 5 units. The capacity means here the maximum capacity, okay? So we are talking about the maximum capacity in the third column. The unit capacity in megawatts gives us the information about the maximum capacity of a particular unit. So for example, 1000 megawatt is the maximum capacity unit 1 can provide. 800 megawatt is the maximum capacity that unit 2 can provide, and so on. So the total maximum capacity is presented here, which is nothing but the summation of all these 5 values. Okay, so it becomes 4400 megawatts. In the next column, that is unit output, means at present how much of the maximum capacity is utilized to serve the demand. Okay, how much of the maximum capacity in numerical value, in number, not in percentage. So in numbers, how much of the megawatt is actually utilized. So is it utilizing all of 1000 megawatt or something less? That sort of information is available here. So under the current circumstances, unit 1 is providing 900 megawatts, unit 2 is providing 420 megawatts, and so on. So one thing to be noted here, that we are considering that all these 5 units are available. Okay, all the units here are turned on or committed. None of them are in shutdown state or decommitted state. All of these 5 units are currently actively participating in supplying the demand. Okay, so that means all of them are spinning. So all of them are spinning. So in total, the total megawatt output currently is 3090. So that is the generation. And for this example, we are actually not considering any loss. So what we have to do here, only we have to satisfy that this generation should meet the demand here. Okay, you see the second last column, regional load. In region 1, I have 1900 megawatt demand. And in region 2, I have 1190 megawatt of demand. So in total, I have this demand 3090, which is again the summation of these two. So my total generation here in this column should meet or should balance out this 3090 exactly. There is no loss. Okay, however, if for any example we consider some losses over these interconnecting networks, then of course we have to add up that loss. And in that case, we have to meet the constraint like this generation, then in that case would be equal to this load plus whatever loss is there. Okay, but in this example, we are not considering any loss. So then we have the regional generation summation of this, because we have 2 regions. So we sum up these 3 values here. Okay, we sum up these 3 values here and we get 1740 megawatt here. And in region number 2, we have these 2 generations, 1040 plus 310. So we have 1350 megawatt of demand, sorry, generation. Again, in total, this number should be exactly same as this number. Okay. Just represented here, it is represented in terms of units. Here, it is represented in terms of regions. That's it, no other difference. So how much is the spinning reserve? How to calculate the spinning reserve? Because there is no losses. So simply we have to deduct this value, this value from this value. So it is 1000 minus 900. So 900 is being utilized for supplying the demand. Remaining 100 megawatt is in terms of spinning reserve. Okay. Similarly, 420 would be subtracted from this 800, the unit capacity of unit 2, and you get 380 and so on. Okay. In the same way, you calculate this minus this, so you get this. Again, this minus this, so you get this. This minus this, you get this, and you add them up to get the total spinning reserve. So at present, under this scenario, we have 1310 megawatt of reserves. This is the load demand provided. Information should be given. 1900 megawatt is the demand in area or region 1, and 1190 is the demand in region 2. So we see that, okay, again, we sum it up and we find that it is 3090, which is exactly matching with our unit output, total unit output. So how much power is actually interchanged between these 2 regions? So to know this, simply you calculate where you have excess power generated. Okay, you just check in which region you have excess power. So in this region, my load is 1900, but I'm only generating 1740. Okay, so that means I'm not generating enough power. So I need some power from somewhere else. So because we only have 2 regions, so the only source of power should be region number 2. So the power should flow throughout these interchanges from this region to this region in this direction. So power should flow in this region. Okay. So the power is interchanged from area 2 to area 1. How much power is interchanged? So whatever is lagging here, okay, how much? 1900 minus 1740. So it gives you 160. So 160 megawatt is coming in. So you see the term in. So 160 megawatt is coming in. So the same amount should come out of area 2. That means you need to produce surplus power here. Okay, your load is 1190, but you have to produce surplus power to meet the demand in area or region 1. Okay, so this is 160 megawatt in going into region 1, and this is 160 megawatt coming out of region 2. Any question up to now?
Sir, region 1 can also use the reserve, spinning reserve. So why not use the spinning reserve of of its own?
Yeah, actually this result, okay, these are not arbitrarily chosen. You can say this is the outcome of some economic load dispatch program. Okay, so probably these numbers, I mean, you can't choose arbitrarily. These are some outcome of some intelligent algorithm or intelligent techniques. Let's say you solve the economic load dispatch and you find that this is the most economic solution at this condition. Okay. However, if you deviate from this result, of course, you can satisfy the demand. Okay, you can satisfy the demand because you have sufficient spinning reserves. You can satisfy the demands. In that case, the production here would be less, but probably that is not the most economic solution here. Okay, you get the point?
Yes, sir.
Okay. Anything else? Because now we will go into contingency situation. Means we will think about, let's say unit number 1 is tripped or out for maintenance. Then what happens? Then we will go to scenario 2. Unit number 2 is out of operation. What happens? And so on. Any question? If this is clear, then I will jump to the next slide. But we have to make this slide clear because we'll take help of this slide every now and then for the next few slides at least for solving the example. So let's go to slide number 14. Now the case is some contingency state, okay, some different states where we consider that unit 1 is out. So you see the red color. Okay, now this unit is tripped or this unit is out due to maintenance. Okay, so is your system or does your system can your system supply the power in secured manner? Okay, in secured manner without hampering the limits of your system, provided limits of your system. So let us see, unit 1 is out, so I've colored it in red. So that means now there is no output. Okay, because the unit is out, there is no output. How much should be the spinning reserve? Out means actually it is not even spinning. Okay, it is out of operation, so it is basically 0. So this thing should be clear. When we are saying one unit is out of operation due to maintenance, means what? If you want to maintain the system, I mean, if you want some maintenance operation, you have to stop, shut down the machine, right? So in that case, you don't expect any reserve in terms of spinning reserve to be present at your hand. Okay, so the spinning reserve is 0. So now your regional load is still 1900. We are not changing the load demand throughout our example. So regional load remains same. So your regional load in region number 1 is 1900. Regional load in region number 2 is still 1190. Still your total demand is 3090. So somehow you have to make sure that this column, the summation of all these again gives you the same value here. Okay, this is number 1 point. So there could be different ways. Again, I'm saying there could be different ways, but the logic here, which the book is following, they will try to satisfy the demand from its own region first. Let's say what I mean by this. If some unit is out of operation from region 1, so what they do, they first try to get as much as possible from the spinning reserves available from area 1 or region 1. Again, for unit 2, if unit 2 is out, they will try to satisfy the missing generation from the spinning reserve available from region 1 and so on up to unit number 3. And for units 4 and 5, they will try to meet the demand or missing generation. They will try to fulfill the missing generation, fill up the gaps with the help of the spinning reserve of region number 2. Okay, first, and then they will try to look out for help to the other region. You get my point? Okay, let me go through the numbers, probably then it would be much clearer. So if unit number 1 is out, how much generation you are missing actually? So you are missing basically 900, right? You see, I have shifted, I have gone to the previous slide. So 900 is missing now. If unit 1 is out, you are missing 900. So if I try to fill up this gap from this region, because we are in region 1, we are missing some unit in region 1. How much can we get maximum from spinning reserve? Anyone can answer this? If 900 is missing, means we don't have this unit. So what is the 760? Excellent. So I can only take these two because I have lost already this. This is no more available, remember. As I have lost this unit, so this 100 is no more available. Only these two are available in these regions. So 760 I can get. So this I will take at first. Still, how much is left from 900? So 900 minus 760 is 140, right?
Yeah, 140.
140. So then I will check here. Okay, I can take mixture of these. I can take any one of these. So here this example is not for economic load dispatch issue. This is just to show you the, theme of spinning reserve. Okay, so here probably you can take arbitrarily. But where the problem arises, I will show it explicitly. Okay, where the problem arises, I will show it explicitly where the problem will come. So another 140 is missing. Have you followed the calculation? I have 900 missing because unit 1 is out of operation. I can get maximum 760, so I will take it first. So 100 is still missing. Remember, unit 1 is missing. So 100 I don't have actually in the next slide. So 760 I will get, but I have to satisfy 900. So I have to take help from region 2 of about 900 minus the summation of these two. So that is 140. So let's say I take 140 from this. Okay, 140 from this. In this way, I can satisfy the demand. This is one solution, but there could be other solutions, of course. But this is one solution. So let's see. So you see what I have said, actually we have done it here. So this first two, they are taking whatever spinning reserves were available. So you see it is updated now. Previously I had only 420 or 420 here. I'm taking up all the available reserves. You see now no spinning reserves. It is 380. I have taken 380 out of 380. So it is already available here. Again, the next unit 380, I have already taken 380 out of it. So it is taken here. Okay, so spinning reserve for these two units are 0. Here my unit outputs increases and accordingly my regional generation increases. Clear? These two becomes 800. Summation of these two is 800. Summation of these two is 800. So total it is 1600. Okay. So as I said, I have to meet up another 140 from somewhere. So because we only have another region, so I can take from there. So accordingly, this value increases. Okay. In this example, I'm taking this 140, remaining 140 from this. But as I said, this could also be taken by a shared manner or from this unit, but that would come from some economic load dispatch program. Okay, that would come from some economic load dispatch program. But here I'm just, the book is not intended to show you the essence of economic dispatch here. Just this example is just for showing you the essence of spinning reserve. Okay. So let's say we have taken 140 from this unit because we can. Okay, how much was available there? 160 was available there. So I can take 140 from this one. So I am deducting that 140 and I'm shifting that 140 here. So my generation of unit number 4 increases. Now it becomes 1180, just the summation of these two. Plus I had this there already present. So I have take it So the total is 1490. So you see 1600 plus 1490, it becomes equal to your demand. And what happens there, because I'm losing my spinning reserve, so my spinning reserve reduces to this 290 here in unit number 5 and whatever available in unit number 4. So I just add them up and just fill up the blanks here. Clear? So what about the interchange? Remember in the previous case we had how much? 160. So now in addition, I have to supply this 140 to region number 1. So in total, this becomes 300 in and 300 out. You can simply also calculate it from here. You see the load is 1900. You can only produce 1600. That means you require another 300 from somewhere. And that is only available from region 2 here in this example. So that means these 300 should come from this, okay? And here also you should match this value. You should have some excess amount of 300 megawatt available between generation. That means 1490 minus 1190. This should also give you 300 here. Similarly, 1900 minus 1600 should also give you 300 here. So still the power interchange is happening in this direction. But now if unit 1 is out, you are of course having some reduced amount of spinning reserve and some increased interchange of megawatt between region 2 to region 1. Clear? So let's move on. Now what will happen if we have, instead of unit 1, if we have unit 2 missing? So let's see. So now unit 2 is missing. So its capacity is 800. So there is no output from there. So you see a zero, red zero there. No spinning reserves is available. These things are already discussed, how these are happening. But now how much is missing? That is the important information. Due to the loss of the unit number 2, how much is missing? Let's check the first slide of this example. You are missing 420, okay? 420 megawatts. So that amount has to be managed from somewhere. So can we manage from this region? Yeah, 420, you can easily manage from this. Okay, this is not available, sorry. So I have 100 and 380, so total is 480. So I can manage. Is that clear? This would not be available because unit 2 is lost. So my spinning reserve would be 100 and 380, 480, okay? But my missing generation is 420. So I can simply take values from this one, some from this one, and then I can meet up this missing 420. So this is what is done. I'm taking 100 from unit number 1. Okay, so there's no spinning generation. So my previous generation in the first slide of the example was 900. So I'm adding the remaining 100 available from the spinning reserve. So now the spinning reserve remaining is 0. And the missing generation is 420. So I need another 320 here. So this and this adds up to the missing generation. And simply I add these 900 and 100. So this becomes 1000. I add this 420 plus 320. So it becomes 740. So total is 1740. I don't have to do anything here. So there remains as it is. And this spinning reserve reduces because previously available reserve was 380. Now I am taking this 320 there in the actual output. So my spinning reserve is reduced. And because there is no flow, no increased flow from this from the region 2 to region 1, so 160 remains as it is. Because whatever change is happening, it is happening within this region. So there is no change here. Clear? It remains at 160. Unlike the previous slide, in slide 14, it increased to 300. Whereas the original one in slide 13, the interchange was 160. Okay. Any question here? Okay, no question. Thank you. So let's move on. What happens if unit 3 is out? You see, unit 3 and unit 2 are actually identical. Okay, if you go to slide 13, they are identical. You see 800 capacity. Unit output is 420, unit 3 output is 420. So they're simply identical. So similar kind of thing will happen. Okay, just unit 2 and unit 3 status will be interchanged, and everything else, I mean, you say just simply they will interchange their role here. So I mean, it is self-explanatory. There is nothing to be discussed. You still have 160 in, 160 out. Simply this unit will be red colored because this is out of operation. This will change their position. So in the previous slide, you see it was 0 and 740. Now in this slide, it is 740 and 0. And accordingly, you can calculate. Okay. Unit 3 and unit 2 are identical. So nothing exceptional happens there. Now let's move on to region 2. Okay. So how much is missing? If unit 4 is missing, we have to go to slide number 13, which is the starting slide for this example. So if unit 4 is missing, I have a huge chunk of power missing. You see, 1040. That is the maximum amount missing among all the units. Okay, this was the maximum power. This was the unit supplying maximum generation. So if unit 4 is missing, we are missing the highest chunk of power. So let's see what happens. So you are missing 1040, right? How much can you take? We go to slide 13 because that is the original slide. Okay, so if you miss 1040, as I said earlier, the first target would be to try and meet the missing generation from here, okay, from this from its own region. How much is this?
450.
450. So how much is remaining?
Just 290.
590, right? That means if you take up all the available spinning reserves, you get only 450, but you are trying to satisfy the missing generation, meet up the missing generation of 1040. So if you subtract this summation of these two from the missing generation, then you get the remaining generation required. So if you subtract,
Sir,
Sir,
why are you considering the spinning reserve of the generator that's not available?
okay, sorry. So thank you. So only 290 is available. Okay, excellent. So only 290 is available. I mean, you can supply. So how much remaining? This 1040 minus 290, right?
Sir, 750.
750. Can you take it from other area? Yes, we can, right? We can. We have sufficient because all these 3 units are available. Okay. So let's say we divide it accordingly. We take some from here, some from there. So how much actually you need to have from here additionally? I mean, you have 290, you can supply 290 here only. The remaining amount, okay, let me check. There is probably mistake I'm making. Yeah, just a minute, let me check. So this is 290 plus 300. Yeah, okay. So we have, yeah, you can make your question now.
Okay, my question is like the region 1 is not self-sufficient, so why going there and taking?
No, region 1 is self-sufficient because region 1, you have
the regional load is 1900 and the regional generation is 17400.
no, but still you have sufficient spinning reserve to satisfy the demand, total demand. Okay, you have sufficient reserve to satisfy the total demand, right?
Yes.
Your final target, what is your final target? Your final target is to make this 3090 equal to this.
Okay.
Okay, so although currently region 1 in this case, okay, in this case it is taking power from region 2, but it has its own capacity, it has some capacity.
Yes.
And now we are in some what should I say, abnormal situation. We have lost unit number 4, and that was providing us the highest amount of megawatt which is missing now. So you have to do something so that we can, in some way, we can use up this. We can also use up some portion of this to make this again 3090. You get my point? Because I'm missing 1040 now. So I have to take, of course, I can take 290 from here, but I have to also take help from here. Okay, the first question is, can I take from here? Okay, does it satisfy this demand? The answer is yes. Okay, I can. Because if I subtract 290 from 1040, how much is remaining?
750.
Yeah, around 750. Okay. So do I have 750 here? Yeah, I have around how much? 760, 860 I have. Okay, so I can, if needed, I can. But the problem happens here. Let us see. Okay, let us see. The problem happens here. So, so what we are doing, basically, this is missing. Okay, so first of all I take this 290. Okay, so this 290 will not be available anymore. So let's take this 290 over here. So how much is the total generation now here? It is only 600. Okay, I mean, if I look it in other way around, only I have left 600, right? I mean, I have available 600. What is my regional load? It is 1190, right? So to satisfy this regional load, how much more do I need? How much help do I need from region 1? This minus this, right? So how much is that? It is 590. Okay, so somehow I have to manage 590 from this region. Okay, I have to manage 590 from this region. So the question is, can I mean, do I have sufficient reserves? The answer is yes, I have sufficient reserve. I had 380 here, I had 380 here, and I had 100 here. So I take 100 from here, I take 380 from here, and I take 310 from here. So the main part is I need 590. Okay, I need 590 help from here. Now I have sufficient reserves, but the problem is that my interconnection cannot carry 590 megawatt. Do you get the point? The interconnection is not able to carry this power. So although I have reserves, I can satisfy my own demand here. Okay, remember, as one of your friends said, I had some lackings here. Okay, I had 160 lackings. If I go back, I had some lackings here, 1740, 1900. Okay, so it was, I mean, I have to now use the reserves in such a way that some part of the reserve will go to satisfy this, and some part of the reserve has to satisfy the missing generation. Do you get the point? Some part has to satisfy this from here, and some part has to go and meet the remaining 590, which is missing here. Okay. Okay. So now the interconnection cannot carry more than 550. So that is the critical number. My interconnection is designed to have a capacity of 550 megawatt. So if unit 4 is out, your current spinning reserve, although it is sufficient, but it is not supported by your network or interchange. Do you get the point? Because the capacity is 550. Although you have sufficient capacity, you can play with this. You can take help from this side. You can only generate 290 here. You can only take 290 from the spinning reserve. The remaining demand has to be taken from other region. So while you try to do that, you find that actually you need 590 in, simply 590 in. So that means 590 should be out of this, and that means this interchange should carry 590, but it is not possible. So if unit 4 is out, you are in a trouble. You get the point? Till unit 3, it was fine. You were fine. There were no troubles. Okay, you were fine. There were no troubles in unit 1 when unit 1 was out. There were no trouble when unit 2 was out. There was no trouble in unit 3 is out. But unfortunately, unit 4, which is basically the largest contributor under current scenario, it cannot give you sufficient, I mean, it cannot give you some secure operation. The operation will not remain in secured condition. What about unit 5? Unit 5 is not done, but of course you can check it. Okay. Unit 5 has a very low participation, 310. So actually, if you solve it, you will find that it is not causing trouble. So the only troubling unit is this. So you should handle this unit with proper care. Okay. So with this example, we have some idea about the spinning reserve. What I actually did probably made you a little confused. In the first portion of my lecture, I started the calculation from the missing generation, right? And in the later part, I switched to missing load. You can also consider it the previous calculations from the missing load, okay? So that you can think it in a uniform manner. So don't get confused. Simply start your calculation, back calculation from the missing, whatever amount is missing, okay? So if you have, let's say 1900, okay? If unit 1 is out, how much you have to satisfy? 1900 minus 900. So accordingly, you can also, in the same manner, you can try and solve it, okay? So with this, let us go to a new topic. But still, if you have any confusion, you can clarify it later on, okay? Just go through the lecture. If you still find any confusion in calculation, because once you try to calculate, then I think once you put your hands on it, once you try to go through this example, then probably some more confusion may arise, which have not come during my discussion. So if you have any kind of confusion, please let me know. Okay, I'll try to make it clearer, sharp. So now we have only covered one of the constraints that is related to spinning reserves, but there are other constraints. Okay, there are other constraints associated with specifically thermal power plants, thermal units, thermal generating units. One of that goes with the thermal unit constraints. This is the title of the constraints, and under this umbrella, we have different types of constraints. First of all, we have a constraint named as minimum uptime. Okay, what is this? This says, let's say one of your unit is running and it is supplying power. Okay, everything was fine. So you should not turn it off immediately. It means what? It means basically, let me try and draw one diagram to make it clearer. Okay, by this what is meant, let's say at time t equals to 0, okay, let's say this is time, this is time. In the x-axis you have time, and in the y-axis, let's say you have unit status, which can be represented by 1 or 0, right? Because unit can be either fully on or fully off. Either it is contributing or it is not contributing. Either it is connected to the network or it is not. Okay, so let's say at time t equals to 0, you turned on the unit because you needed it. Let's say your load increased suddenly. Okay, so if your load increases, you have to turn on the unit. So this was the transition from 0. It went up to some one value, 0 to 1. So this is 1. Unit is on. What minimum uptime says, that let's say within very short time, if your load decreases, then you cannot turn this off within a very short time. Okay. What I mean is this. I mean, let's say you just turned it on because load increased, then you suddenly saw load decreased. So you can't make it, I mean, very abrupt. You just turned it on. You have to allow some time before you decide to turn it off. So sufficient amount of time should be given to the unit once it is turned on. So this distance is known as minimum uptime. Once a unit is on, it should be allowed to run for a sufficient period of time. This is minimum uptime. Okay. What is minimum downtime? Minimum downtime is the reverse case. Once a unit is off, you cannot suddenly, as I did earlier, you cannot suddenly at zero instant, you cannot turn it on again. You just turned it off, let's say. Okay, let's say one unit was running like this. Okay, this was a running unit. So you just turned it off because the load decreased. Okay, let's say at this time instant, the load decreased. So you turned it off. Of course, satisfying this minimum uptime. Okay, let's say minimum uptime is satisfied. Now you are encountering or facing another trouble. So you shouldn't just turn it on again within very quick duration, within very short duration. Okay, you should allow the unit to be down for some instant of time, and then only you should allow it to turn on again. Why is this necessary? Any idea? I mean, why you should allow the units to keep running for some time once it is turned on, and again once you turn it off, why should your unit be allowed to cool down for a certain period of time? Any idea?
Mechanical rotations.
One is associated with the rotation, because your machines are actually a large inertia, right? You can't expect a step change like this. Okay, you have a very big machine, megawatt range machine. The inertia is very high, so you can't expect it to operate in this way. This is one thing. Another thing is that the boilers and the turbines which are associated with your generators, the boiler, you see, your boilers are to be heated up. You have already visited Gorashal unit, big boiler unit. It takes hours to get heated. Okay, and then again it takes hours to get cooled down. So there is temperature change. Okay, abrupt temperature changes on the boiler wall. Let's say it is made of some material. So if you try to make the temperature changes abruptly, basically what will happen there, it will work as impulses on the material. Okay, temperature or thermal impulses, we can say thermal impulses. So suddenly you see you are trying to reach 1000 or 2000 degrees Celsius, and then again you are calling, okay, cool down now. Then again suddenly after within very few seconds you are saying, okay, now again heat up. So this is not possible. Okay, so that will create fatigue on the material, on the boiler material, whatever material is used for manufacturing the boiler. And also that will create pressure, okay, pressure difference, abrupt pressure difference on the turbine blades, because sometimes within very short time you are actually trying to put force on the turbine blades, and after within very short time again you are trying to reduce the pressure, suddenly taking the pressure off. So there is a pressure change, you can say change of pressure with time. Again, there is change of temperature with time. This should be not very high. In short, we can call it like this. We can, in summary, we can define these two things like this. So you should allow sufficient time for your boilers and turbines. You should allow your boilers to cool down for sufficient time. You should allow your boiler to heat up for sufficient time. Okay, only then you can think about turning the unit off or turning the unit on. Okay, not before that. So these are associated with minimum uptime and minimum downtime. What is crew constraints? Crew constraints means as a company owner, okay, what you would like to do, you would like to have a minimum, what should I say, minimum, you should try to spend minimum amount of money and you try to extract maximum amount of profit, right? So your management department should make a study that, okay, what is the minimum, let's say, minimum amount of crew required to run the plant in normal condition, let's say, okay? So if that means you cannot choose the number of crews available, you cannot make it very high, because in that case, most of the time, probably the crew will be sitting idly, okay? The crews will be required mostly when probably you have some maintenance work, or units are shutting down, or units are being committed or decommitted, okay? So if you have, let's say, more than 2 or more units, they cannot both, okay, multiple units cannot be turned on or turned off at the same time, probably because you have not employed sufficient crews, because you want to save some money there. Okay. So this is not related to technical things. This is basically related to monetary issue, economical issue. Okay. But if you have sufficient money, okay, if you say, okay, I want more crews there, okay, so that I can operate whenever required, I can turn on the units whenever required. I have sufficient crew for each unit, okay. That is to say, I have sufficient crew for each units. Generally, that is not the case. Generally, they reduce the number of crews so that only when it is required, they employ wherever possible, just to save money. Okay. So this is not actually, you can say it is some economical constraint, okay? Some economical constraint. Okay, so again, this is probably some of your earlier explanations that I give. The temperature and pressure of the thermal unit must be moved slowly, as I mentioned. A certain amount of energy must be spent to bring the unit online. Okay, what does this mean? Certain amount of energy must be spent. You have to expend certain amount of energy to bring the unit online. What does this mean? This basically means that some amount of energy you will also require to fire up or to heat up the boiler unit, okay? For example, because the energy that you are spending to heat up the boiler, that energy is not converted, actually not converted from mechanical to electrical finally, which is your required output, okay, electrical output. So you have to heat up your boiler for some duration and you have to burn fuel there. So that amount of energy is required to only bring the unit online, okay? And after that, you will be able to supply some electrical output from your generators, not before that. Again, this is associated with the thermal units, okay? For hydro units, probably specifically this issue is not there. So if you are spending money there, okay, you are not producing any significant megawatt out of your machine because your machine has not yet started producing power, only your boiler has started to heat up. So this cost specifically is termed as startup cost. So this specific cost is required just to start your system, okay? Just to get your system running. Before even producing power, just to make it able to produce, you have to spend some money, and that cost is known as startup cost. So this startup cost can be again categorized into two. One is hot start cost, another one is cold start cost. What is hot start cost and what is cold start cost? Okay, before I explain it, let me ask you a question. What do you think if I have a unit, okay? As I know that a unit requires hours, okay? Big units, big thermal units requires hours to actually get running or to be able to supply power, right? Some time is needed. So what would you do when, let's say, your algorithm gives you the information, okay, now you can turn the unit off? What would you do? would you allow your unit to completely become cool? This is one way. Okay, you shut the unit, you shut your turbine unit, you shut your boiler unit, you shut your generation, you shut everything, and allow your unit, boiler unit, to become cool at ambient temperature. Okay, that means sufficient amount has elapsed to allow your boiler unit to cool down. Okay, the unit is not operating, it is in decommitment stage, decommitted stage. You have allowed sufficient time to for your boiler to get it cool down, completely cool down. This is one way to decommit a unit. Okay, but what is the problem here? The problem here is that when you commit, when you try to commit it again, then you have to start from the scratch, right? You have to start from the zero. What I mean is this. Let's try to draw a diagram here. I mean is this. Let's say this was your temperature here. Okay, the unit was running at certain temperature. So now your algorithm gives you the information that, okay, unit commitment solution gives you that, okay, at this instant of hour, you don't need this unit, so you turn it off. So what you do, you simply allow the unit, okay, up to this point, the unit was running. Okay, so then you allow the unit, of course, that it will take some time to the temperature to get cooled down. Let's say this is the ambient temperature. It is not zero. This is the temperature scale. Okay, so along this line, this is your, let's say this is your ambient temperature. Okay, so your unit gets cooled down at this temperature. Okay, so what is the problem? The problem is that when you will need this unit again, means when, let's say, the load has changed, the load has increased, so you have to turn it on again. So what is the problem here? Basically, you have to again allow sufficient time, something like this. Do you get the point? So only after this point of time, you can have some efficient or effective output from the unit. If you allow the unit to get cooled to some ambient temperature here. Okay, this is, so whatever cost will be associated here to bring your unit from the ambient temperature to some let's say 3000 degrees Celsius. Okay, this high temperature, whatever cost is needed, this is called start cost, because you are starting your machine, starting over your machine from the scratch, from the, you can say, the cold status, the ambient temperature. Okay, clear what is cold start cost?
Yes, sir.
So now can anyone say what is hot start cost? Okay, what is the problem here? The problem here is that actually when you go from here to here, again, you have to burn some fuel, right? To increase this amount of temperature from the ambient temperature, let's say from 20 to 25 degrees Celsius to 2000 degrees Celsius, you have to burn some fuel, of course. You have to heat the boiler continuously to reach the boiler temperature from that low value to this high value. So there is some cost, cold start cost. What about the hot start cost? So another way to look into the problem is this, the hot start cost. Let me draw another figure here. The hot start cost is, let's say your unit was running. So it was at some certain temperature, right? It was at some certain temperature. So now you decommit the unit. Okay, that means you decommit the unit. You don't need that much of fuel input, of course, because you have decommitted the unit. So unit is not providing you any significant megawatt output. So of course, the required heat would be less. But what you do, you try to maintain the temperature at some low value, just to keep the boiler temperature near to your operating temperature, final this temperature. Okay, so you spend some fuel here continuously, on a continuous manner, just to maintain this temperature. You get the idea? So that when it is required again, You just need this amount of time and you can simply go for production. So here you are not allowing your boiler to get cooled down to the ambient temperature by supplying some fuel, not 100%, whichever was required for this production, not that amount of fuel, but some reduced amount of fuel will be required just to maintain some temperature, high temperature for the boiler, so that when it is needed again at this instant, you can simply do it within very short time. This is hot start cost. That means you are starting your unit from some hot boiler, okay, not this cool boiler, cooled down boiler. Rather, you are starting it from some hot status. So you can say this is hot status for the boiler. This is the cool status for the boiler. But of course, in both cases, money is involved. In this case, on the right side, for the cold start costs, you have to spend the money here, okay, but not here. On the left hand side, for the hot start cost, you have to spend the money here, significant money here, and little money here. Do you get the idea?
Yeah. So the trade-off is needed.
Yeah, a trade-off is needed. Trade-off is needed. Excellent. So with that, so as an engineer, you have to decide which one is beneficial for you, for a specific unit, which option you should go. So now let's do some mathematics. I mean, try to derive some formula with these two costs. Very simple formula. So on the y-axis, we have the startup costs. This you have some fixed cost. What is this fixed cost? This is not associated with heating up or cooling of the units. You can say this is the other cost, operational cost of the unit. Okay. This is some sort of fixed non-zero cost. And then the one I'm calling the cold start, is the hot start cost. The hot start cost, what I said, on a continuous basis, you have to supply some fuel, right? Throughout the off period, let's say in the x-axis, we have the time in span in hours. So on a continuous basis, you have to keep the temperature at the same value. And that's why your cost is increasing as it is being multiplied with time. It is a linear function of time. Beyond this CF, it is simply a linear function of time. As time goes on and you are continuously keeping your unit at some specific temperature, so you have to keep your fueling on. Okay. So this is a simple formula at the bottom. So startup cost, when this is called banking. Okay. Another terminology is for hot start is banking. So you have some fixed cost CF. This is simply y equals mx plus c, that sort of formula. Okay, y equals mx plus c. So you have the fuel cost, you have the time span during which this span, okay, in the y-axis, how much time you are keeping your boiler unit at some specific temperature, and the CT is the cost of maintaining unit at that operating temperature. Now about the cooling, if you have not, you have not cooled it, okay, you have not cooled it for sufficient time, let's say 0 time instant, that means you have not actually cooled it. So this T value here, you see the T value at the top inside at the exponent, this is exponential basically. So this T value, this is 0, right? So if this is 0, what do you get? You get simply e to the power 0 is 1. So simply this will vanish and you get CF. So if you have not cooled it, that means you are at this point, okay, at the fixed cost point, right? Now, the more you cool, the more the cost will be, right? The more amount of time you cool it, the more will be the associated cost to bring it back to the operating temperature. And this is what this portion says. Of course, when it reaches the ambient temperature, let's say at this point, you see the curve getting flattened. At this portion of the operating temperature, let's say it has reached the ambient temperature. So the cost will not vary beyond that. Let's say the unit takes around 5 hours to get cooled down. So if you keep it cool, keep it off for 6 hours, 7 hours, 8 hours, the cost will not vary because it has already cooled down, right? But before that, the cost will vary according to this expression. Okay. And this alpha here is basically the thermal time constant. That means the time it takes to reach to 66 point, around 67% of the final value, like any other time constant for any other topic. So it is observed that if you compare these two, okay, which option should I take? So there is the answer. As one of your friends said, you should go for some trade-off. So there is the answer. At some specific hour, you see some crossover point, okay? So that means beyond this or before this point, if you're operating, if you're cooling your unit for this duration and then you are turning it on, it is better to go for banking. That would reduce your cost. On the other hand, if your cooling period is more than this, then of course you should go for cooling so that you can save some money, okay? Any question? No. Okay, so there are some other constraints put in short, like must run unit. That is to say, if let's say if you are owner of a power station and you have some other customers other than producing power, you are planning, okay, let's say I have some steam getting out without any reason. Okay, so can I earn some money from that steam? So what you did, some of the other industries, they require this steam. Okay, they are a small industry, they don't want to spend money for buying the boilers and other things to produce this steam. So what they do, they make contract with you. They have a contract that you will supply that amount of a specific amount of steam for a certain duration of time. Okay, let's say in certain specific period in the year, okay, not continuously. So that means that unit becomes for that specific time, because you have contract with that small industry that you will supply steam to them, which is of course which is not required by you. So that extra steam or additional steam, you have to produce them. Okay, so besides producing steam for your own generation, own generating plant, you have to supply the steam to some other small industrial organizations or industries so that they can continue their production. And because you have a contract with them, you cannot decide to turn the unit, boiler unit off. Okay, so that in that case, that specific unit or units becomes must run unit. Do you get the point? What is a must run unit?
Sir.
You had some contract, so you have to supply the steam, so you have to produce the steam for your generation, own power generation, plus the generation you want to help them, of course, at the expense of their money, so they will pay you. So you're actually selling the steam. Okay, so you have to produce the steam at that time. So for that duration of time, you can't turn your unit off. You cannot go for decommitment. These units are known as a must run unit. Of course, this is only one example. There could be other examples. You can look for those. But this is one example where you may have a must run unit. You cannot turn it off for that duration of time. Fuel constraints, of course, you may have limited capacity of storage. Okay, let's say you need the coal. So although the supply is there, but maybe you don't have sufficient storage capacity. This is one way to say fuel constraints. Okay, another way to say you don't have sufficient money to buy that amount of fuel at a time, so you can't store that amount of fuel, and so on. So that means you may also come up with some constraints on your availability of fuel. Okay, availability of type of fuels. Then hydro constraints comes, of course, if you are considering a parallel operation of hydro units as well as thermal units. In those cases, probably these constraints will come, but because we are not taking it in this course, so I'll not go into any discussion of this. Okay? But of course, if you are looking for hydrothermal coordination, these hydro constraints are to be considered. Okay. So with all these constraints, of course, there are some other constraints, but let us start with this. If we come up with some new constraints while we try to solve the examples, then I will explain it there, okay, on that specific moment. Not, I think we have discussed enough constraints, but if something is left, probably we can add those in due time, whenever needed. So now what are the solution methods? Very older methods, pretty older ancient methods are probably the priority list schemes. Then accordingly, historically, dynamic programming was used, which we will take, the first two we will take in this course. But of course, we also have Lagrangian relaxation. You can go for mixed integer programming. As we said in earlier part of the lecture, in the previous lecture, we said about the mixed integer programming. Okay, what is mixed integer programming? Whenever you have some continuous variables as well as some integer variables, decision variables, which will provide you the optimal solution. In those cases, we call the programming problem as mixed integer programming. Okay. So you can also take help of mixed integer linear programming, MILP techniques. Of course, the list is much more extensive. Okay, I have not listed, but there are other methods. In the book, they have mentioned these four. In the textbook, they have mentioned these four. I will go with this priority list and dynamic programming, just to make the idea clear. Okay, probably I will take time. Okay, I will take this probably in the next class. I have only 4 minutes. Okay, so let me stop here. So again, let me give you the announcement. The quiz will be starting at 8. The quiz will be posted in the Google Classroom under the title quizzes. Okay. So under the title quizzes. Now, before you leave again, please put your IDs as soon as possible, because I see on after each class, someone is still hanging there. I don't know why. So please try to put your IDs and leave the class so that I know that, well, everyone has left, then I can stop the meeting. Otherwise, I have to hang around and wait for those guys. Okay, so please make it.
স্যার
Yeah.
স্যার সাকলাইনের নেটের সমস্যা করতেছে, ও একটু আগে ডিসকানেক্ট হয়ে গেছে, সো ও মেসেজ দিছে, ও এতক্ষণ ছিল স্যার।
No problem. Is he 167?
116.
Oh, there is another message from 167. Oh, this is message is about previous class. Okay, no problem. So what I do actually at the end of the class, I wait for some time, but even after that time, I see someone is still hanging there. I just write their IDs in the chat box, press enter, and just keep it recorded so that later on I can check back and find out who were present. Okay, but still I will request you to just put your IDs in the chat box and please leave the classroom if you don't have to ask. If you don't want to ask anything, please leave it so that I get my participant list cleared up, and I can close the meeting. Okay, thank you.
Assalamu alaikum, sir.
Walaikum assalam.